I'm Suzanne Stone. I work for DeMarTech. And most of you know my boss, Dennis, and I believe Jen is on this call. I'm just going to talk really quickly about the power source. If you can move to the next slide.
Suzanne, we'll get slightly better video if you make your slides slideshow full screen, but if that's a problem, this is okay.
Like that?
That's great.
Thanks, Wayne.
Good.
So DeMarTech is, as you can see on our screen, a test lab specializing in real-world hands-on research and analysis of data center technologies. Just offhand, we do a lot of storage and server tests. We are an ISO 17025 accredited test lab, EPA recognized for Energy Star data center storage testing, and we're a SNIA recognized tester. If you want to visit our website, that link down there will take you to a nice video that if you wanted to go through us to have your testing done, it explains the process because there's a lot of parties involved. There is a CB, there is ourselves and the EPA and the customer, of course, that wants their stuff certified. So there's a lot involved there. So if you're interested, click on the link. Next slide, please. So my main thing that I'm going to be covering has to do with the fact that with the new version of the spec, SNIA Emerald has adopted the power standards that Energy Star always had. Since most people were submitting for Energy Star, most of us have done this and made sure that our voltage and total harmonic distortion was within the tolerance ranges. But just to review, and since it's new to the SNIA spec, if you're operating at below 1,500 watts, you have a voltage tolerance of plus or minus 1% and total harmonic distortion of plus or minus 2%. Okay, thank you. And if you're operating above 1,500 watts, you got a little more leeway. You have plus or minus 5% voltage and plus or minus 5% total harmonic distortion. They also have allowed voltages. The ones that we work with the most are 115 volts and 230 volts. Most people would like to certify at 230 volts because it tends to be a bit more energy efficient. So if you go to the next slide. So when we look at our wall power and we're operating at, say, 230 volts, our wall power is coming in at 239 to 241 volts. And we work with smaller systems, so it needs to be within 1% of that, which we can't do, which is why we need a power source. We also see the THD vary considerably. It not only depends on what's coming in from wall power, but also what equipment is plugged in. Anybody that's looked at this will see typically the odd order harmonics on storage systems or servers or anything like that will get amplified. So next slide. And here we have on the top left, you can actually see your harmonics. That's your first order harmonic all the way over to 50. This is from our Yokogawa power system, or power analyzer, excuse me. And you can see, you know, the first order, this is a logarithmic scale on the left. And you can see most everything's in the first, but then if you look at, there's nothing on the second, but a lot on the third, nothing on the fourth, a lot on the fifth. This is following the typical pattern that you'll see with some digital systems, also a slight shifting of the phases of the voltage and amperage. So that's just an example of what you'll see, and this is with a source. You'll notice our function on the right-hand side, U, and you'll see the data says that it's currently, when this screenshot was taken, at a max of 230.31. So obviously we're not on wall power. And it's hit, while this has been recording, a max of 230.31 and a min of 230.31. So it stays pretty tight when you have it on that source. But yeah, you still get some harmonic distortion. You can see that at the bottom of the right-hand side with UTHD and ITHD. UTHD is the total harmonic distortion of your voltage, and ITHD is the total harmonic distortion of your amperage. So we're very lucky that most of the time what we care about is the UTHD and not the ITHD. Otherwise, we would be out of spec. Next slide. Now, typically, I just want to make sure that people that are thinking about hooking up a source or hooking up their power meter need to be respectful of the power of electricity. Typically, 100 to 200 milliamps doesn't kill you, but if it was administered directly to the heart, it would. Your skin and other things are a great insulator, but the amount of insulation that it provides varies greatly depending on different characteristics of the environment. So just please be careful when you're doing this. If you don't know what you're doing, please hire someone to train you or get an electrician. I think that most larger test houses would do so. We just trained our personnel well, and we make sure there are two people, one to set up and one to check everything after setup to make sure there's nothing wrong, because we don't want to lose anyone. Next slide. So we have this cable pictured here, and that is what's going to hook into the output of the power source. That's the 3 connectors on the left. The middle section is the part that goes into your analyzer, and then, of course, the last section will be what your storage will plug into. And, of course, whenever you're setting this up, make sure nothing is plugged into wall power. Just do it with no power going through. Thank you very much. Next slide. So here you can see on the left is the output for your source. On the middle is where you're hooking it up to your power meter. And on the right is where we actually put it into where we're going to be plugging our storage into. Of course, it has no storage yet, but that's where it's going to go. Next slide. This is the one that will actually go to the input for the source. So you're going to hook up those 3 prongs on the right first onto your source and not plug them in, please. Next slide. So here they are. This is the input for your source. Check your work or have someone check your work. And then next slide. Most equipment provides handy little clear guards, so you can still see how everything is hooked up, but it lessens your chance of accidentally shocking yourself. And as you can see, we're not plugged in yet if you look on the right. Next slide. Once we are plugged in, we need to power on our source. For this particular source, which is a Chroma programmable AC source, we have to go to the Setup menu. Next slide. Once we go to the Setup menu, we can enter in our voltage. You can see VAC equals 230. You can enter in the frequency, which on this one needs to be changed. Once that's all set up, we will press the Out button, and then you will see the light turns on to show us that we're actually sending that current out. Next slide. Once you plug in and turn on your power meter, you will see that we are dialed in at, according to this particular shot, 230.26 volts. And of course, we can use the function keys on the right to adjust which parameter we're viewing on the displays. Next slide. Any questions?
Hello, this is Chuck. Yeah, I have a question. This is some poking around that we did way early on in the process. Did you folks do any sensitivity analysis of varying the THD and observing what happens to the power consumption when you vary that?
It seems that when you vary the THD, we couldn't control it very well from the source, but we've had some products that, depending on how many power supplies we had plugged in, it would vary the THD for us. And it seems that when THD increases, your power factor will go down, and I think that's why they're concerned about that, right?
Yeah, that's the same observation that we had early on. It's really counterintuitive because what you said, the power factor goes down. Yeah, so we observed actually something a little different than that. We observed that when the THD went up, I believe the studies we did shows that the power factor actually improved, which means that the energy efficiency improved when the THD went up, which is really counterintuitive. We never, come to a religious agreement on that, but just early on observations.
Yeah, I guess it could go either way because a lot of that THD comes from the storage that you are testing.
Right,
so,
and other things that are plugged in there, right.
Yeah, well, and the other thing on that, Chuck, is it depends on whether your power factor was leading or lagging.
No, I understand. Yeah.
Because the harmonic distortion can move it, but if it's moving it down and you are on lagging, then it'll go down further. If you're leading, it'll bring you back to lagging.
Okay.
That's why that's where things get weird.
Mm-hmm. Yeah.
That's one of the things we don't make note of is whether the power factor is leading or lagging. So.
Right.
Yeah, I hadn't thought about that, but it was brought up in another totally different context earlier on a different call.
Mm-hmm. Yeah. Thank you.
Thanks.
Any other questions for Suzanne, or any other experiences that want to be shared from one of your own labs?
So what software are you using when you're reading that meter? Because I'm pretty sure you're not hand scribing it off the front panel.
So that is the Yokogawa software that works with their analyzers.
Okay, that'd be like WT Viewer.
WT Viewer, what it used to be called. Yeah. Uh-huh.
Okay.
And Suzanne, this is Samuel from MetLabs. When you guys are doing your measurement, do you say your voltage? I mean, your voltage is set, but do you say your current ranges, or you leave it on auto?
I think we just leave that on auto.
Is that what Met does today, or do you observe differences by auto versus manual?
Well, I know for some measurements, when you leave it on auto, the accuracy of the meter is compromised because then the it's jumping all over the place depending on what your current measurement is. We had not for storage, but for servers, when we did run spec power, which the EPA doesn't use anymore. When you have it set on auto, you do get some invalid results.
That's very interesting. Yeah, I haven't seen that with the storage. Usually the amp is not varying enough to have it bounce in and out of different ranges, but I can see how that could be a problem.
I can definitely see that with servers.
Yeah, with storage, I don't think it's a big issue because the current draw is pretty much stable and consistent, whereas in servers you have it jumping all over the place.
Okay, that's a good point that you brought up. Because in the future, like you think about, we have these systems that are called hyperconverged systems, and we add those in a taxonomy. It might be something we'll have to look closer at, so, since it could be configured as a server or storage, or it has both attributes in the system. All right. Any last questions?